Good morning, everybody. My name is Thomas, and today I'm going to be presenting differentially private simple genetic algorithms, and this is joint work with my supervisor, Florian. So I'm going to start with a very quick overview of differential privacy. So this is a very intuitive guarantee that basically one person's data shouldn't have a huge effect on the outcome. So if I do some data analysis with a person's record or without, the result should be basically the same. Now this is a little bit informal, so let's get a little bit more formal. Specifically, I want to solve the selection problem in differential privacy. So this is where I have a data set of users' data. I have a whole bunch of candidate solutions, let's say different machine learning models, and I have a utility function that maps the data set and the candidate together. How good of a fit is this for the data set as a real number? You can think of it as loss or something like this. And then what I want to do is I want to choose a candidate that maximizes this utility function, but I want to do it in a private way such that the probability of picking this with a person's data or without is bounded by e to the epsilon. So the most common way to do this is using the exponential mechanism. And so what this does, you just basically draw sample your candidate following the formula I have here. It's based on utility, epsilon, and sensitivity. But the problem with this is that you have to kind of compute this bottom sum, which is over the whole domain. This can be quite expensive, especially when the domain is huge. Like think of all the different possible logistic regression models. So the solution in the literature right now is to do subsampling. So just basically take a random sample of the domain and then run the exponential mechanism. But the utility can be bad because you're just uniformly sampling here. So what we want to do is we want to come up with a new solution that's private, efficient, general purpose, and accurate. Basically efficient, I mean I want it to be sublinear in the domain. General purpose, I want to kind of have the niceness of the exponential mechanism that I can kind of plug in whatever utility function. And accurate, but I think that one's self-explanatory. So I'm going to talk about genetic algorithms. So just a recap of that for people who are not familiar. So basically at GA, what you do is you randomly generate a whole bunch of solutions and you iterate on them. You essentially evolve them like we evolved. And so what you do is you have some selection based on this utility function. You pick good parents. These good parents make children. You basically combine two previous solutions to make a new solution. There can be random mutations. So basically this will generate a whole new population. You'll kill off the old population, and the new one survives. And the idea is that over time, you should get a good population, essentially like we got humans. And basically, the whole reason this works is this selection is picking good parents each time. So why should we use them for the selection problem? Well, the runtime is sublinear. I just do some fixed number of generations. So it's efficient, yay. I have minimal requirements. A GA can work on non-differentiable functions. It can kind of work on most utility functions, so it's general purpose. And there's been work showing it is robust to noisy objective functions. So in theory, it should be accurate. But is it private? And it turns out yes. And basically, all you have to do is modify the selection step, because this is the only part that uses the data. So you swap out the selection for a differentially private one. And someone's done this. In fact, they did it in 2013. So this is the first differentially private GA, and so what they do is just basically swap out that selection step for the exponential mechanism. And the thing here is we're going to do a lot of generations, and we do a lot of selections. This takes a lot of privacy budget. We want to do more selections in order to evolve longer and get a better population, but each selection costs us something in DP, so there's this trade-off. So what the previous work does is they use a truncation top K selection. So we basically pick a smaller number of candidates each time and save some privacy budget. And this is nice. But there's some problems. Somebody else evaluated it later, and they were like, differentially private GAs are not very good at all. They get terrible utility. And kind of the reason they thought why is because basically the operators can be very destructive in this particular GA, like the previous one. So basically, they didn't allow a good solution to survive. So if a solution was good, there is no way that it makes it to the next generation, and that's kind of bad. If you find something good, you end up getting rid of it. And also, it took a lot of generations to converge. As I mentioned, there's this trade-off, so the utility ended up being quite bad. We also evaluated it ourselves, and we found out it often does no generations at all, and this was kind of crazy. They have this formula here about how many generations to do, and when you plug in all those numbers, it's almost always 0. So this basically means you just initialize a population, pick a candidate, and you're done. And this is not great. We want to do the evolution. So this is our evaluation of that. So on the y-axis, I have utility, or negative loss. So higher is better. And on X, I have the optimal number of generations with a little star, and you can see it's always 0. So this wasn't just a bad parameter choice. This is actually the best for their algorithm. So this isn't great. So what did we do? Well, we decided to kind of start from scratch and redesign this because we wanted hope for genetic algorithms in differential privacy. So we figured out ways to reduce the noise, which I'll talk about. We figured out ways to protect these good candidates, stop them getting destroyed. And we did a lot of experiments on like the different hyperparameters, how they're affected by privacy, and comparisons and things like this. So this is our algorithm. I'm not going to get into details. I just want to point out a couple things. So first of all, you'll see what I highlighted here is we replace the selection operator for a DP selection operator, which can be anything, exponential mechanism or alternatives like noisy max. And what we do is we first select a small set of parents. So this is like 10 parents out of maybe 200 solutions. And then when we want to pick parents after that, we'll just uniformly pick from the bag. So this means we use a bit less budget. And this is what we copied from the other guys. This is from the previous work, because we thought this was great. What we changed, a few things. One is that we took this good set of solutions and we initialized a new population with that. This is called elitism in genetic algorithms. And so this, basically fixes that problem. And we also added more standard operators, because kind of this previous paper did a bunch of things that were weird and not typical of the GA community. And so we did things like add probability of crossover, which again stops things from being destroyed, and used better crossovers and things like that. We did a pretty extensive evaluation, but this part was how to reduce the noise of DP. So we looked at various options for what to use for selection. So exponential mechanism, noisy max, permutant flip, that's a newer one. We also looked at different composition theorems because there's kind of different assumptions and it's not really obvious which one would be best with which because there's trade-offs. And finally, reducing the sensitivity of the utility function. So usually you'd use like cross-entropy loss for machine learning, for example, but GAs can optimize the accuracy or the 0-1 loss directly. And that's a counting query, so it's got nice low sensitivity. So basically, these three choices I have in red turned out to be the optimal ones and gave us a nice advantage. And so with that and all of our operators, we reevaluated, and you can see this is the same graph as before. But for us, we have this nice kind of slope that you would expect. So epsilon is on X, or no, generations are on X, and the epsilon is the different colors. But what the trend you're seeing is as epsilon increases, I can do more generations, and that's kind of what makes sense, right? So with a higher epsilon like 3, I could actually do 150 generations, and that was the best choice. So yeah, GAs make sense, and I can do crossover and things like that. Okay, so the evaluation I was talking about. So we evaluated against a whole bunch of different work. First of all, PrivGene, so that's that first genetic algorithm solution. There was also some local search techniques. So this is just an iterative kind of greedy algorithm. Turns out there was a few of these for the problems we looked at. But I don't have time to talk about that today. We also looked at efficient exponential mechanism alternatives. That's the subsampling I mentioned, so taking the random sample. And also, each of the problems I considered, there was literature that was like problem specific. Like this was their jam, and we looked at those as well and see how we were against that. So the two problems we looked at, logistic regression training that we mentioned, and also the k-medians, or facility location. So this is like I want to open some stores in a town. So I have a set of possible locations for my like grocery stores. I have a private database of users, and I basically solve clustering, but it's restricted to this set of possible stores. It's like a discrete k-means in some way. And it's a nice non-convex problem that we could study. Okay, so first of all, let's look at prior work. So here we have utility again on y and epsilon this time on the x. And as we go higher on y, we get more utility. And as we go further on x, we get less private. And as you can see across the whole parameter of epsilons, we beat this previous work significantly. We've kind of fixed a lot of the problems. And that's great. Thank you. So we'll skip local search. We'll go to efficient mechanisms of subsampling. Is here in blue, and you can see this kind of plateaus. And this plateau is basically the error due to subsampling, and we can't get around that, right? So whereas our work is able to scale better with epsilon and get a much better performance. Finally, let's talk about problem-specific techniques. So we benchmarked against a whole bunch of convex optimization techniques like DPSGD and things like that. And kind of the conclusion we took is we're competitive. So on the graph on the left, you can see we're doing quite well. we're outperforming it. I have 2 lines there. One is where I tuned the hyperparameters, and one's where I didn't. Because obviously the tuning gives you better performance, but it would cost you something. The related work also cheated and tuned their parameters, so that's why I have that there, so it's kind of like a fair comparison. But yeah, and on the other data set, we're a little bit less. This is why I say we're kind of in line with something that's tailored for the problem, which is nice. And the same thing was true in K-medians, but I don't have time to talk about that today. So with that, I'll conclude. So we have shown that despite previous results, GAs can kind of have a place at the table in the DP selection problem. We've proven they're private with a privacy proof, which is quite simple. It's basically composing the exponential mechanism proof a bunch of times. Efficient, up to 20 times faster than some of the problem-specific work we looked at, such as K-medians. General purpose, we evaluated a couple problems, but it's quite easy to tailor it to any problem. You just need a utility function that's bounded, and that's about it. And finally, accurate. We saw a significant improvement over the previous work, but also we were kind of competitive with the main players that were problem-specific. And with that, I thank you and welcome any questions.
Thanks very much. Again, please ask your questions in Zulip if you can. We can start with one in person, too.
Okay, hi, thanks for your talk. Can you go back to, is it still possible to go back to slide 15?
we just switched to the next
Great
one.
question, right? Sorry about that. So on slide 15, as you vividly remember,
Yes.
So you had a kind of a plateau, right,
Yes.
on the right graph. I was intrigued by that plateau because it looked like you didn't make much progress beyond a certain value, right? And yet you seem to be happy to go until, let's say, 150 generations. So can you please elaborate on that?
So is this the subsampled mechanism one?
Right.
So the blue line that plateaued was actually related work, right? And ours does plateau a little bit, but not as much. Basically, the plateau for them is because they randomly subsample from the population. And so like when the domain of solutions is so huge and you just take a small uniform subsample, your chance of actually getting the good machine learning model is pretty slow. It's basically like I did 10,000 random initializations of a machine learning model and picked the best. And so if I only did 10,000, I'm kind of limited there. So that's the flaw of related work, whereas for us, we did more, and we can kind of iteratively get past that plateau.
Okay, I see. Okay.
Yeah.
All right, okay, thanks a lot. Yeah. Thank you.
Let's see. We have a question online, which is, do you think that the advantage of the exponential mechanism over the permute and flip comes from the fact that you can compose the exponential mechanism via bounded composition, and you can't do that with permute and flip?
100%. So that's why we evaluated all the combinations. So at first, like if you look, permute and flip is much better than the exponential mechanism, but there's been results that show you can't use bounded range. And bounded range ended up, because we're doing so many generations, that ended up being the dominant factor, was the composition. So even though permute and flip was a bit better, and is a bit better, yeah, this was basically the combo that made the most sense.
Got it. And so for somebody who is totally not in this field, can you answer a question? So cool, your thing is much faster than somebody else's.
Yes.
Can you relate to this some practical application for me? Is it something that previously didn't work, now works in reality, or we're now 5 years closer to it working in reality?
It really depends on the problem. So yeah, I think for something like, for example, these K-median problems where like, in machine learning, we've had DPSGD, so that's kind of already got a solution and we're competitive with it. But for like the clustering, the best we had was this subsampling, right? All we could do was either brute force the whole domain, which was just completely infeasible, or we could take this random shot and get terrible utility. Whereas now, we can kind of get something in between, I think. So I think it's those types of problems, especially the harder problems that don't have gradients and things like that. Now we've kind of got a bit better solution for something like that.
Great. Thanks very much. Let's thank the speaker again, please.
Thank you.